Okay, well, so we are here today, of course, to celebrate the 50-year legacy of the Apollo program when humans first set foot on the surface of our moon. However, we're also here today to celebrate the next 50 years of space exploration, hence the name of today's event, Apollo 50 plus 50. Those next 50 years belong to a new generation of scientists, engineers, and explorers. It is today's students that will become the leaders of tomorrow. They are passionate, they are diverse, they are extremely motivated, and they will take humanity further than ever before. We're extremely proud to introduce to you 9 of our current students who will each present a short 4-minute lightning talk. These speakers are all volunteers, and they were selected from a larger set based on the fit with today's topic, the quality and the impact of their research. The lightning talks have been sequenced in a way that will take us on a journey starting with our home planet to its vicinity, including the moon, then Mars, our solar system, and even beyond. At the end, we will ask you, our audience, to vote for your favorite lightning talk. So without further ado, please give a warm welcome to the next generation of space pioneers.
Good afternoon. There are emerging opportunities in space-based communication systems that no longer limit us to the radio frequency portion of the electromagnetic spectrum. Our ability to communicate through light using optical communication systems enables us to transfer large amounts of data, both from our satellite to the ground, as well as in between satellites on orbit via optical crosslinks. My name is Cadence Payne. I'm a second-year graduate student in the Space Telecommunications Astronomy and Radiation Lab under Dr. Carrie Cahoy. What I'm talking to you about today is one of the many projects, emphasis on many, in our lab called the Laser Crosslink Atmospheric Sounder, or LCAS for short. So LCAS is actually capitalizing on this emerging technology and applying it for a scientific application. So LCAS is comprised of 2 3U CubeSats. CubeSats are satellites that are about the size of a loaf of bread for reference. So our plan here is to take these electronic bread loaves, we're going to throw them into space, separate them by a fixed range, and then make them talk to each other via these optical links. So as they'll be chatting with one another, they're going to occult or go behind the Earth. And in doing so, that optical crosslink will sound the Earth's atmosphere, giving us information about what's comprising these regions. So the really cool thing about these optical links is that you're actually able to tune them to look for species of interest. And the one thing that we're most interested in looking at is water vapor. So I know what you're thinking. You're like, water vapor, like, why would we care about that, right? We know that there's a lot of water vapor up there. However, as I'm sure, hopefully, you guys are all aware that the Earth's climate is rapidly changing. So as the Earth's climate changes, it actually has adverse effects on the convective storm systems that we experience down here on the ground, such as thunderstorms. So climate change is actually causing our thunderstorms to increase in both intensity and frequency. And this increase is causing the convective transfer of water vapor into regions of the Earth's atmosphere where it doesn't naturally exist in large quantities. So the region that we're most interested in looking at is called the upper troposphere, lower stratosphere. So as these water molecules are moving into this region, they're hanging out with the ozone molecules that live there naturally. And as they're parting with one another, they're creating something called chlorine monoxide. And as I'm sure you're also aware, the Earth's atmosphere is increasing in temperature, right? So this warming, in conjunction with the presence of carbon monoxide that doesn't naturally live here, is actually working to catalytically destroy the Earth's ozone layer, which is a problem. Right? The ozone layer is our primary protector from the harsh UV radiation of the sun. So as it's eaten away by this effect, there's an increase in probability of us experiencing harmful effects such as skin cancer. So we're not claiming that we can combat climate change with our tiny little satellites, right? That's not feasible. However, what we can do is monitor and quantify this effect using our emerging technology. So we have two tools in our toolbox. The first is actually something called a bending angle that we're extracting directly from our optical link. And the second is using a differential wavelength mechanism to actually compare and contrast our measurements. So in the previous image, you saw that there are actually 2 beams of light there, right? So Angela Cruz in our lab has done a bit of analysis in a program called ModTran. So what you're seeing here on this graph is actually both of the wavelengths that I just mentioned in the second tool. So the first in the red box is showing the optical link directly interacting with the water molecules that live in this region. So the depth of the dip in the box directly gives us information about how much water vapor lives in this area. The second box here is actually representing the second wavelength and the differential pair mechanism. And so you can see there's very little attenuation here, meaning that we can actually use this as a reference. So it's these two tools that allow us to measure both the concentration of water vapor as well as the increase in temperature simultaneously. And this is critical for us to understand and monitor this harmful effect on our ozone layer. So to us down here on the surface of the Earth, the atmosphere is all-encompassing, right? It touches every part of the Earth that we're able to see. However, to the astronauts that we're here celebrating today, they have a much different perspective of what the atmosphere looks like, right? So from space, you're able to see both the magnificence and the fragility of the Earth's atmosphere. And because it's done such a good job at protecting us, to the point of even allowing us to exist on this tiny blue dot in the universe, now it's our turn to put in the time and effort to understand the harmful effects that we're causing so that we can do a better job at protecting it in the next 50 years. Thank you.
My name is Rachel Aniceto, and I'm a doctoral student in the Space, Telecommunications, Astronomy, and Radiation Lab, working with Professor Carrie Cahoy. In 2015, astronaut Scott Kelly tweeted, "Connection speeds on the International Space Station are worse than what dial-up was like." On Earth, we actually have the technology that allows us to transmit and receive data at rates of hundreds of gigabits per second inside of fiber optic cables over long distances. This is 1,000 times faster than what we're currently providing our astronauts. Today, we are significantly limited in the data capacity and throughput required for the high amount of scientific data we're collecting on space missions, and as we propose for missions over longer communication link distances. Free space optical communication, also known as laser comm, can enable high-speed communication in comparison to radio frequency or RF communication systems typically used on our satellites today. Similar to fiber optic communication, laser comm uses light as its medium for carrying data. But instead of propagating inside of these fiber optic cables, this light propagates through free space. In this image on the slide is NASA's Mars Reconnaissance Orbiter, also known as MRO. We heard earlier today that the mission of this spacecraft is to take high-resolution images of the Martian surface, with one of these high-resolution images equivalent to about 7 HD movies. So MRO uses a radio frequency communication system and transmits data using that 10-foot wide antenna you see on top of the spacecraft. At a data rate of 6 megabits per second, it takes an hour and a half for MRO to send just one of those images back to Earth. However, if we were to replace that system with a laser comm system of similar size, weight, and power, MRO would be able to transmit one of those images or 7 HD movies from Mars to Earth in under 5 minutes at a data rate of 100 megabits per second, 17 times faster. On top of that, you can get rid of that bulky 10-foot wide antenna that you see on top of the spacecraft and replace it with just a half-foot telescope aperture. So laser communication can be an approach to our need for high-throughput communications, and it has actually already been demonstrated in space. In 2013, NASA and MIT Lincoln Laboratory demonstrated laser comm from the LADEE spacecraft orbiting the moon to Earth at a data rate of around 600 megabits per second. We're now talking around 42 HD movies from the moon to Earth in just 5 minutes. There are ongoing efforts used to develop laser comm, such as for the NASA Psyche mission and even for the Orion module for future crewed missions. So the key challenge that we face now is, although this technology now exists, we must make sure that it can meet the competitive cost points of the radio frequency communication systems typically used today. In MIT Star Lab, our solution is to develop a high-throughput optical communications modem for space applications. Specifically, our strategy is to use commercial off-the-shelf components from terrestrial fiber optic communications industry. These are the same lasers, receivers, electronics, ASICs that are in your data center modems. This enables two things. The first being a high data rate. This optical modem is capable of transmitting and receiving to space missions at rates of 200 gigabits per second. This is about 30 times faster than current state-of-the-art of what's been demonstrated by laser comm systems in space. Second, this also achieves a low-cost modem, enabling us to have a bill of materials cost of less than $50,000 in comparison to the modems that have already been demonstrated that are specialized with space-grade parts and range up to hundreds of thousands or even millions of dollars. So we have achieved this modem through 3 key steps. The first is through radiation testing and characterization. In this middle image is our hardware prototype of an optical modem that transmits and receives up to 200 gigabits per second of data. We've taken this to the NASA Space Radiation Laboratory, which you see on the left-hand side, and we find that this technology survives harsh space radiation environment, specifically heavy ion radiation. Through characterization of how this technology behaves to radiation effects, we can now use software and firmware mitigation techniques. And finally, with mechanical and thermal design principles, we can ensure that it can meet space mission requirements. In Starlab, this optical modem and our developments in laser comm are enabling the next generation of communications technology that will allow us to further achieve our missions in space exploration. Thank you.
Hello, everyone. My name is Matthew Moraguez, and I am a doctoral candidate here at MIT in the Engineering Systems Lab, as well as a NASA Space Technology Research Fellow with the Marshall Space Flight Center. And today I'm going to talk to you about in-space manufacturing. So ever since the launch of the first satellite, Sputnik, back in 1957, all through the Apollo program and up until today, every single satellite to orbit the Earth has followed the same exact paradigm. It was built on Earth, launched aboard a rocket, and then operated in space. Now, this framework is clearly limiting for space system designers who are trying to design an orbiting satellite, but are forced to consider the strenuous launch environment in their designs. One development that can potentially revolutionize this paradigm is in-space manufacturing, also known as ISM. With ISM, we carry out the fabrication, assembly, and integration of components in the orbital environment in which those components are intended to operate. Because components built by ISM are not limited by launch-related design constraints, ISM can promise to reduce the cost and improve the performance of existing space systems, while also enabling entirely new capabilities. So inspired by these promises, numerous companies have naturally sought to pursue commercial in-space manufacturing. Some notable examples shown here include the Grumman Beam Builder, which carried out a ground-based demonstration for the production of large aluminum trusses with a welding and forming operation. The Made in Space Additive Manufacturing Facility, which is a plastic 3D printer currently operating on board the International Space Station. And the SpiderFab concept from Tethers Unlimited that hopes to use additive manufacturing along with robotic assembly to produce extremely large structures in space. But a key challenge facing any of these commercial ISM ventures, and the reason why many historical attempts have failed, is the difficulty of achieving the correct pairing of components to be produced by ISM and the manufacturing processes used to produce those components. So this leads to a key research question that we hope to answer here at MIT, which is, first of all, what are the best application areas for in-space manufacturing? And then what are the technology developments needed for the manufacturing processes used to produce those components? To answer this question, we first identified the launch-related design constraints that are relaxed when we use ISM. This allows us to determine the in-space manufacturing application areas that have the potential to provide a benefit over the existing launched approach. Some examples of these areas include the production of large structures that no longer have to fit within launch vehicle fairings, lightweight structures that no longer have to survive launch loads, unique products that can only be produced in the space environment, and even the on-demand manufacturing of spare parts. Now, this spare parts fabrication is of particular importance for the future of human spaceflight because it will allow us to travel further into deep space for longer durations than ever before, such as on future Mars missions. But it's not enough to simply identify these areas where ISM has the potential to provide a benefit. So we've gone forward with developing cost estimating relationships and performance models that allow us to determine the exact break-even point beyond which ISM surpasses the existing launched approach. We are now developing physics-based manufacturing models that will allow us to determine the size, weight, and power required for this manufacturing equipment. And then we can utilize these models to ultimately optimize that combination of components and manufacturing processes for any given application. As a result of this research, we've been able to evaluate the commercial viability of ISM across a wide range of application areas. Some of the most promising cases identified by this work include the production of solar array support structures and the pulling of Z-band optical fiber, as shown here. Now, we believe that armed with this framework for determining the best components to be produced within space manufacturing, and with these models of the manufacturing processes themselves, that in-space manufacturing can be developed to a point where it can truly revolutionize the future of spaceflight. Thank you.
Hello, my name is Golda Wynn. I'm a graduate student in the Human Systems Lab, and like all of you, I've been inspired by moments like this. I'm sure you know the photo. This is Neil Armstrong working at the base of the lunar module. Just moments before in the mission, he had stepped down from the ladder and said those famous words we all know and love. Before I came to grad school, when I heard this quote, I mostly thought about how incredible it would have been to be in his shoes that day. Now that I'm in grad school, I mostly think about, well, how much range of motion did he have when he stepped off? How far could he step off? How small of a step are we talking about here? That's because in the Human Systems Lab, a lot of our research focuses on turning the qualitative into the quantitative. So today, I'm going to talk about some of the research we do on characterizing human motion for medical and aerospace applications. So in my lab, I work on utilizing wearable inertial measurement units to develop metrics of human motion. IMUs are typically used in the realm of navigation to provide you information about the orientation and rotation of a moving object. So when that moving object becomes a human, not only can we understand information about their joint orientation and their limb movements, but we can also start to get at the underlying techniques of motion and performance. I specifically work in the realm of clinical therapy. I work with patients that have previously suffered a stroke and experience reduction of motor function on one side of their body. These patients will go through occupational therapy, and they'll work with a clinician to perform rehabilitation exercises to help regain that motor function. During these exercises, a clinician is going to assess how they're moving during the activity and their overall performance and progress during the task. However, those assessments rely on the expertise of the clinician, their familiarity with the patient, and their ability to assess them in person qualitatively. So this is where IMUs can come into play in providing quantitative support for those qualitative assessments. In the lab, we've been conducting pilot studies with patients wearing IMUs and motion data or motion capture devices so that we can start to understand how can we translate this data into intuitive metrics that we can pass to a clinician so that they have tools to help provide and support their decisions in future studies. So now you might be wondering, how does clinical therapy relate to astronaut performance? Well, it turns out the metrics that we're developing for patients can be translated into understanding how astronauts are moving on EVA and then as they're performing activities out on terrain. As astronauts are traveling further away from the Earth, we need to equip them with tools to be able to independently and non-invasively monitor their movements and activity as they're out performing geological sampling, traversing across terrain. And IMUs present an avenue where we can provide metrics and assessments to monitor them as they're moving around. We're hoping that in the future, they're going to be able to not only maneuver around, but then also be able to have communication devices back to where they are. As we look toward the next 50 years of space exploration, it's becoming increasingly beneficial to continue to highlight these intersections between aerospace and external fields like medicine. As we look toward those next 50 years, we want to be able to not only help astronauts out there, but make sure that we can translate those tools to helping astronauts back here. In the HSL, we're working to enable new modes of patient health assessment and monitoring. And in turn, we want to enable astronauts to go do these incredible things out in space and then come back to Earth in good health and live out long, healthy lives so that in 50 years, they can continue to inspire us in the way the Apollo astronauts have been doing for the last 50. Thank you.
Hi, my name is Lena Downs. I'm a master's student in the AeroAstro department here at MIT, and I'm also a Draper Fellow working jointly with MIT's Aerospace Controls Lab and Draper Labs of Cambridge, Mass. Today, I'm going to tell you about lunar terrain relative navigation. NASA has stated that one of its strategic goals is to land a US astronaut on the surface of the moon again. In order to reach this goal, Draper Labs has been awarded a commercial lunar payload services contract, and I'm working on the navigation team for this effort. The problem is that as we return to the moon, we would like to visit more interesting locations. But more interesting can often mean more hazardous. For example, if we want to land near the edge of a crater so that we can explore it and determine its age and origin, then we need to avoid landing on the highly sloped rim of the crater. But there's no GPS on the moon, and it's actually pretty difficult to figure out where a spacecraft is without GPS. Previous lunar missions have relied mostly upon inertial navigation, which integrates acceleration and velocity measurements from IMUs and accumulates drift quickly from round-off errors. Lunar landings have had landing errors as high as several kilometers. This means that we can't confidently plan to land too close to the edge of a crater because we risk landing in or on the crater. In the Apollo 14 mission, the main goal was to explore the Cone Crater in the Fra Mauro Highlands. The lunar module touched down approximately 1,400 meters away from the crater, here. Astronauts Alan Shepard and Ed Mitchell trekked the distance on foot, the equivalent of 14 football fields, while wearing spacesuits that were very difficult to maneuver in. They got to within 30 meters of the edge of the crater, at which point they were forced to turn around due to low oxygen levels. With higher precision navigation, it would have been possible for them to land somewhere like here. One way to achieve higher precision navigation is through terrain relative navigation. Terrain relative navigation is the process of sensing the terrain beneath a vehicle and using that information to update your estimate of where the vehicle is. I'm working on a team from Draper to develop a camera imagery-based terrain relative navigation system for low lunar orbit to landing. The way that we'll use camera imagery for terrain relative navigation is through crater detection. This image is representative of what the downward-facing camera of a spacecraft would see as it enters low lunar orbit. We have a general estimate of where our spacecraft is from previous inertial measurements, and we also have a database of craters on the moon with their sizes and locations. With this information, we can expect to see these craters in our camera image. We have the latitudes and longitudes of these craters. We can also visually process our camera image to detect craters using a variety of methods, like convolutional neural networks and traditional computer vision methods. For example, we can perform thresholding, which is the operation of setting the brightest pixels to white and the darkest pixels to black, and edge masking, which is the process of finding the edges where pixels change color. This allows us to get our crater detections. We know the relative locations of our detected craters to the spacecraft because we detected them from on board. By combining our detected craters with our known database craters, we can get our crater matches. Our crater matches tell us the absolute location of the spacecraft in the lunar coordinate system. And by repeatedly incorporating this measurement into our navigation system, we can correct for inertial drift and achieve much higher precision navigation. I'm currently researching how to optimize the number of craters that we detect, as well as the percentage of those craters that are true crater matches. In conclusion, terrain relative navigation will allow us to explore more interesting locations on the moon using higher precision navigation and safer landings. Thank you.
Thank you. Can we survive on the frozen, nearly airless Martian tundras? My name is George Lordos, and I'm a PhD candidate in the Engineering Systems Lab, working on sustaining human life on the planet Mars. I'm here today on behalf of our team to tell you about Project Hydra, our proof of concept system for mining water ice on Mars. 50 years ago, Apollo spacecraft carried all the water needed by the crew on their journeys to the moon. But missions to Mars will last 100 times longer, at least. So NASA is interested in utilizing water that is already there. One promising opportunity is to extract water from subsurface ice, which has been discovered at various locations around the red planet. In response, we designed and built Hydra, a dual auger system. The outer hollow auger is driven through the regolith down to the ice, and is driven through the regolith down to the ice by a passively coupled mechanical system. This system consists of a rod and a spiral groove. Coupling rod, spiral groove. From there, the inner auger continues descending into the ice and breaks it up and lifts it to the surface. Simplicity and easy manufacturability were very important guiding principles for our team. The outer auger has been additively manufactured, coated with epoxy, and capped by a steel cutting bit, right here at the bottom. While the water filtration system can be cleaned simply by reversing the pump. One key result was that this plastic auger that you see here has remained intact after 12 hours of competitive drilling through compacted clay and gravel. Also, our final paper describing the path to flight has been awarded the best technical paper at the 2018 Mars Ice Challenge Forum at NASA Langley. I would now like to share with you a short video showing Hydra in action last summer. Commander Hadfield, you have control, sir. Take it away.
This is ground control to Major Tom. You've really made the grade. And the papers want to know whose shirts you wear. But it's time to guide the capsule if you dare. This is Major Tom to ground control. I've left forevermore, and I'm floating in a most peculiar way, and the stars look very different today. For here am I sitting in a tin can, far above the world. Planet Earth is blue, and there's nothing left to do.
Thank you, Commander. Not finished, one second. Sorry. This year, a new team of MIT students is developing a new concept, hydration. Hydration will drill through the ice, melt it in place, and pump the water up to the surface. Our team looks forward to contributing to water extraction techniques that may one day be used to sustain human life on Mars. Thank you.
Hello, everyone. Thank you for having me. My name is Eric Hinterman, and I am very passionate about human space exploration. I'm fortunate enough to work on a pretty exciting project here at MIT that I'm going to share with you all. And I hope that you're ready, because today I get to teach you how to make oxygen on Mars. So I want to send people to Mars. I'm sure a lot of you would like to see that happen too. Perhaps some of you thought it would happen a long time ago. My hope is that it coincides with the right point in my career where I can help to lead that effort. And because of these ambitions, I've spent a lot of time researching why we haven't sent humans to Mars yet. It turns out one of the biggest reasons is cost. I have a question for you all. What is the most important thing about sending future astronauts to Mars? You don't have to answer, it's okay. Obviously, it's making sure that we figure out how to bring Mark Watney home. We don't want to forget him there. But did you know that it costs over $1 billion to send the propellant to Mars that will bring astronauts home? $1 billion. That doesn't include any of the other aspects of the mission, just the cost of sending the propellant to Mars that astronauts will burn in a rocket to get home. We should bring our astronauts home, well, at least the ones that we actually like. But $1 billion is a staggering number and a major roadblock. So what can we do about it? In situ resource utilization, or ISRU, is often called living off the land. It essentially means using the resources that you have at your destination site to make what you need. If it costs so much to send the propellant to Mars, why not just make it there? I'd like to introduce MOXIE, the Mars Oxygen ISRU experiment, which is here to solve our problem. MOXIE is a prototype that is actually launching to Mars next year on NASA's next rover, and it will demonstrate ISRU on the surface of another planet for the first time ever. MIT and JPL are teaming up to lead this effort, and we actually hand MOXIE off to the integration team next month. While on the surface, MOXIE will demonstrate ISRU by converting the atmosphere into oxygen. And this oxygen can be used as rocket propellant to fill a Mars ascent vehicle and bring astronauts back home from Mars. Now, I told you I would teach you how to make oxygen, so let's get to that now. MOXIE uses a key technology called solid oxide electrolysis to convert carbon dioxide into oxygen. This oxygen, like I said, can be burned as rocket propellant. Fortunately for us, the atmosphere of Mars is 96% carbon dioxide, so there's plenty to go around. The system works as follows. A compressor on MOXIE pulls in the atmosphere of Mars and compresses it before passing it into the solid oxide chamber, which is preheated to 800 degrees Celsius. Now, once in this chamber, the gas is flowed over an electrode, and a voltage is applied to the stack. Under these conditions, carbon dioxide will break down into carbon monoxide and oxygen ions. The oxygen ions will actually diffuse through this stack, and while the stack prevents carbon monoxide or carbon dioxide from getting through. Therefore, on the other side of this stack, we get greater than 99.6% pure oxygen to use as rocket propellant. MOXIE is just a prototype. A version about 150 times larger than it could be used to support the first crew of 4 astronauts on the surface of Mars. Some of the challenges involved in scaling this up to full size include the high power requirements of the system and potential degradation of this electrode stack with repeated cycling. My PhD research is focused on figuring out how to optimally scale MOXIE to a full size in order to support humans. MOXIE is here to prove that we can make oxygen on Mars for the first time ever in order to knock down one of the primary barriers of sending humans there, which is the cost of bringing them home. Thank you very much, and I hope you will follow MOXIE's progress as it launches to Mars next year and lands on Mars in 2021 to start making some oxygen. Thank you.
Last December, NASA's OSIRIS-REx spacecraft arrived at the near-Earth asteroid Bennu. On board was the REx's spectrometer, built by students right here at MIT. My name is Mark Chodas. I'm a PhD candidate in the Space Systems Laboratory, and I'm the systems engineer and technical lead for RExus. OSIRIS-REx's mission is to bring a sample of asteroid material back to Earth for analysis. The asteroid Bennu is believed to be very primitive, preserving conditions from solar system formation. By returning a sample of the asteroid to Earth, we can look back in time to understand how our solar system formed and the origin of Earth's organic molecules and water. OSIRIS-REx launched in 2016, arrived at the asteroid in December of 2018, and since then has been analyzing its shape, mineralogy, and learning how to navigate around the smallest body ever orbited by a spacecraft. RExus is an X-ray fluorescence spectrometer that will enhance the OSIRIS-REx mission through measurements of global elemental abundance ratios and mapping of elemental distribution across the surface of the asteroid. This information will be used to provide context for the sample. X-ray fluorescence is the process whereby an atom emits an X-ray photon after being stimulated by an incident X-ray photon. The emitted photon has an energy that is characteristic of the excited atom. Therefore, X-ray fluorescence spectroscopy enables measurements of elemental composition. In our case, the incident X-ray photon comes from the sun and fluoresces an atom on the surface of Bennu, thereby allowing us to measure the elemental composition of the asteroid. This technique has been used on many past instruments, including spectrometers flown on Apollo 15 and 16 to measure the elemental composition of the moon. But REXIS represents the newest generation in planetary X-ray spectroscopy. We use CCDs to directly measure the energy of each X-ray photon, resulting in significantly improved energy resolution over past spectrometers. Additionally, we have a coated aperture mask, which allows imaging in the X-ray band without any focusing elements. This is the first application of coated aperture imaging to map a planetary body. Last November, we conducted a calibration observation of the Crab Nebula, and using our coated aperture mask, took the picture that you see on the right of the slide. But the most unique aspect of REXIS is that it was built by students. Since the REXIS proposal was selected in 2011, the team has been mostly composed of both undergraduate and graduate students. Most students have been drawn from the AeroAstro department here at MIT, but students have also come from the Earth, Atmospheric, and Planetary Sciences department here at MIT, as well as Harvard and other universities. More than 70 students in total have contributed to REXIS in some way over the past 8 years, and more than a dozen master's and PhD theses have been written on REXIS. The student team was responsible for taking REXIS from the primitive CAD model that you see on the left of the slide to the flight hardware that you see on the right in only 4 years. REXIS is an excellent example of the conceive, design, implement, and operate, or CDIO philosophy established by the AeroAstro department that emphasizes hands-on project experience, communication, and teamwork. REXIS provides an unparalleled opportunity for students to work alongside industry and NASA professionals in a realistic work environment. REXIS has been working successfully in deep space since launch in 2016. Our main observation period will occur this summer, and I look forward to sharing our data with you. Thank you.
All right, we're down to the last talk. Did you know that there are more planets than there are stars, and at least a quarter are Earth-size, where conditions are neither too hot nor too cold for life? Until 1992, we did not know if there are planets on any other stars besides our own. And today, we know over 4,000 planets, and 60% of these were discovered by the Kepler Space Telescope. My name is Akshita Krishnamurthy. I'm a PhD candidate in AeroAstro working with Professor Sarah Seeger. And today, I want to tell you about 2 missions, TESS and Asteria, that I've had the incredible opportunity to be part of here at MIT, and that are pushing the boundaries of exoplanet science. When a planet passes between the host star and the line of sight of the detector, it blocks a tiny portion of the stellar apparent brightness by a few hundred parts per million. By measuring this drop in brightness, we can detect the planet. An Earth-like planet around a Sun-like star causes a dimming of 0.008% or 80 parts per million, requiring very sensitive instruments to make these measurements. The Transiting Exoplanet Survey Satellite, or TESS, is one such instrument. TESS is a NASA Explorer mission that was launched in 2018 and is led out of MIT. TESS has 4 cameras, and each camera has 4 CCD detectors. The zoomed-in image on the screen is from a single CCD detector. Now, what makes it significantly challenging to detect small planets that may be capable of harboring life is the instrument systematic noise. Now, instrument systematics is significant for very faint stars that have a low signal-to-noise ratio, or very bright stars where there is charge blooming. For my PhD research, I'm developing tools and techniques to precisely characterize these instrument systematic effects, and then study if the detector noise properties can be used to improve the photometric performance. Let me give you a key example. Now, the size of a pixel on a detector is just 15 microns. The response of a pixel varies from another pixel. In fact, the response varies within each pixel. So in the presence of spacecraft jitter, if the stellar image moves from the detector even by a fraction of a pixel, that can reduce the photometric performance. So for my PhD research, I'm using 3-pronged approach. Now, the first is to use flight data analysis and pixel response function measurements that were taken on board on a very high subpixel scale. The second is to use recurrent neural networks, also called the bidirectional LSTMs, or the long short-term memory, to learn the features in instrument systematics by studying photometric variations over time. And the third is to use laboratory characterization techniques to precisely mimic on-orbit operating conditions and spacecraft jitter by precisely moving the stellar image on the detector in subpixel steps. The second mission that I'm applying this very framework to is called Asteria. Asteria is a CubeSat technology demonstration mission by JPL and MIT that was launched in 2017. In fact, Asteria started right here at MIT as part of a course called 16A3, or Space Systems Engineering, back in spring of 2010. Today, Asteria is making science observations and very recently detected the transit of a known planet called the 55 Cancri E, the first ever by a CubeSat. Now, Asteria has a different type of detector called the CMOS detector with very different properties than the CCD detector, requiring very careful characterization of the instrument systematics. Asteria is now performing science observations, so in the summer, I will be performing precise detector characterization of the detectors at JPL. So by complementing flight data analysis with precision characterization of the instrument, we hope to improve the photometric performance of not just larger space telescopes like TESS, but also advance the more economical CubeSats like Asteria to perform impactful science. So with missions like TESS and Asteria, MIT is at the forefront of this giant effort to consolidate our knowledge of what lies beyond the solar system. And I truly believe that it is this generation of MIT scientists and engineers who will answer the key question: are we alone in this universe? Thank you.
Wow, was that not terrific? Well, now comes your time to tell us which of these talks inspired you the most. Yes, but you do have to choose. We have set up this link here, tiny.cc/Apollo2069, as a link where you can submit your vote. So let me remind you the 9 talks you heard. Number 1, Cadence Payne, Laser Crosslink Atmospheric Sounder. Number 2, Rachel Aniceto, Gigabit Class Optical Space Communications. Number 3, Matthew Moragas, In-Space Manufacturing. Make it, don't take it. Number 4, Golda Nguyen, Human Motion Study of Patients and Astronauts. Number 5, Lena Downs, Lunar Terrain Relative Navigation. Number 6, George Loros, Mars Ice Excavation, Hydra and Hydration. Number 7, Eric Hinterman, MOXIE, Producing Oxygen on Mars. Number 8, Mark Chodas, Rexus, the X-ray spectrometer at Bennu. And number 9, Akshata Krishnamurthy, TESS and Asteria, Discovering Exoplanets. So please submit your vote at this time, and the winner will be announced at the end of today's event. Thank you very much.